Let's start with this problem. How much heat must be absorbed by ice of mass m, 720 gram, at minus 10 degrees Celsius to take it to the liquid state at 15 degrees Celsius? So we start from ice. So, well, what we do, we warm ice. We will melt ice. It will turn out into water, that's 0 degree basically. And we want to warm the water into 15 degrees Celsius. So when you draw this, you will recognize immediately that you have three steps: warming the ice, melting the ice, and warming the water. Warming the ice. What is the heat required? That specific heat of what? My state is ice, specific heat of ice. There are different specific heat of ice and water. We just saw it in the table before. Times the mass of ice times the increment delta T. The specific heat of ice, if you go back to your to the table, you will see that is equal to 2220 joule per kilogram Kelvin. It's important to write a unit to not do mistake. The mass of, so this is kilogram, the mass of ice, that's 720 gram, so it's better to write it in kilogram. And delta T, you go from minus 10 degrees Celsius to 0 degrees Celsius. That's how you warm ice, not to 15. 15 there is no ice. So to 0 degrees Celsius. So that's my delta T. What is it? 10. 10 degrees Celsius or 10 Kelvin, that's the same thing. That's very important to know. Delta T in degrees Celsius, that's the same thing as delta T in Kelvin. And you will ask Q1. So we end up, what is Q1? That's basically about 16 kilojoules. So second step, phase transformation, melting the ice. Well, let's call it Q2. That's what? That's the mass of ice. We are melting all the ice, so latent heat of fusion. So latent heat of fusion, that's 333 kilojoule per kilogram, 0.72 kilogram, and this gives you 240 kilojoule. So warming liquid water. Warming water. Well, commonly, when we talk about water, we talk about liquid state. Q3, that's mass. So that's the same mass. Specific heat of what? Of water now. And delta T. So the mass that 0.72 kilogram. Specific heat of water, I will not just write a unit, 4186.8 joule per kilogram. And this one, what is delta T? I go from 0 to 15. So that's very important, this drawing. So that's 15. So you do that, you will find about 45 kilojoule. So what is the total heat now required? The total heat, I'm out of space, so I just write it here. Total heat, well, that's the sum of all the heats. You sum all this up, and you will get about 300 kilojoule of energy required to raise 720 grams of ice from minus 10 degrees Celsius into liquid water at 15 degrees Celsius. Let's see the next question. If we supply only 210 kilojoule, so we needed 300 kilojoule to go to 15 degrees Celsius, water 15 degrees Celsius. Now we have much less than that. We have just 210 kilojoule. What is the final state and temperature of water? 210 kilojoule. So what I can do with that? So ice was at minus 10 degree here. We warm ice into 0 degree. What was the energy required? Q1, that's 16 kilojoule. Okay, for ice to go from minus 10 degrees Celsius to 0 degrees Celsius. Okay, we need this energy. Do I have this energy? Yes, I have 210. I can warm ice into 0 degrees, so I am here. Okay. Second energy required, 240 kilojoule to go to melt ice. I don't have this energy. So basically, after the first step, what is the energy remaining? So I need to warm ice from minus 10 degrees Celsius to 0 degrees Celsius. I use some of the energy here. I use 16. What is remaining? 194 kilojoule. So that's the energy remaining from the first step. This is smaller than Q2, so I cannot melt all ice. I can't melt all the ice. Probably I will melt a part of it. I will use the energy to melt a certain part of it. What it means? Can I go to this? Can I raise temperature? I'm not raising temperature. So my final temperature, what is it? 0 degrees Celsius. I am still melting ice. I have the coexistence of a solid state and liquid state of water. So I am at 0 degrees Celsius. I am at the temperature of transformation. So I have a beaker here, and in my beaker there is ice and liquid water coexistent at 0 degrees Celsius. That's what I have. That's my system. Now the question is, what is the final state and temperature? So we found the temperature, final temperature. Now the final state. Okay, it means, do I have ice, do I have liquid? Well, I just said we have a mixture of ice and water. We have two states here. But in this kind of question, we need to go further. We need to say how many ice I have and how many water I have. Right, that Q remaining, it will be used for fusion. So latent heat of fusion times the mass. Which mass? The mass of the matter that was formed, the mass of ice that melt. Q remaining divided by latent heat of fusion of water, and this will give you, so 194 divided by 333 kilojoule, this will give you 583 grams. So this is the mass of ice that melts. In other words, what is it? That's the mass of water. So the mass of water, liquid, 583 grams. What is the mass of ice that remain ice? Well, that's what rest. We started with, just to remind you, we started with 720 grams of mixture. So what is remaining? That's the difference. That's 137 grams. So that's the final state. All right, let's see now another problem, another kind of problem. We have a copper slag whose mass, given 75 grams, so that's the mass of copper, is heated in laboratory oven to a temperature T 312 degrees Celsius. So we heat copper to 312 degrees Celsius. The slag is then dropped into a glass beaker containing a mass of water, 200 grams of water. So we have a glass beaker with 200 grams of water. The heat capacity of beaker, so we give me heat capacity of beaker, so that's important, 45 calories per Kelvin. The initial temperature TE of water and beaker is 12 degrees Celsius. Assuming that the slag, beaker and water is an isolated system, so that's a very important word, isolated system, and the water does not vaporize, find the final temperature TF of the system at equilibrium, at the thermal equilibrium. Copper, when it was in oven, that's at that thermal equilibrium. The glass and water, the initial temperature, 12 degrees Celsius, that's at thermal equilibrium. When you mix them up, they are not at thermal equilibrium. You need to wait longer so the thing will settle down and you reach temperature equilibrium where all of them, copper, beaker, and water, they will have the same final temperature. That's the second equilibrium state. So basically the first equilibrium state, that's for copper, 312 degree, that's copper, that's equilibrium state. We have 12 degrees Celsius, that's for water and beaker, that's second equilibrium state. When you mix them, they are not at equilibrium state. They will settle down at a certain temperature here, TF. I don't know what is it. That's the equilibrium temperature. But there is an indication here, the water will not vaporize. It means TF is smaller than 100 degrees Celsius. So we don't have a phase transformation. We start with water and we heat it up. We will reach final temperature. And what we have here, do we have steam? Do we have, no, we have water. So we have basically here copper, water, and beaker. There is another word important here. This system is isolated. Okay. So an isolated system, it means that don't exchange heat. So Q of this system is zero, the total Q. Okay. So that's what we will use. The heat is zero. What is the total heat? Well, we have heat of water, heat of beaker, and heat of copper. Let's write it C. Heat of beaker, I will write it just B. So let me make it more simple. So that's plus QC equals 0. Heat capacity of water, the mass of water, times delta T. What is delta T? The water go from 12 to T final. So that's T final minus 12. Plus beaker, we have a heat capacity of the beaker. We have a heat capacity of beaker. So that's CB times delta T, TF minus 12. Plus copper will cool down. So that's specific heat of copper, the mass of copper, T final, always T final minus T initial, 312, equals 0. So this term, it will turn to be a negative term. Okay? And you solve this equation for T final. As simple as that. So you plug all the numbers. When you do that, you will find TF equal to what? 20 degrees Celsius. So the key point, the strategy here is just to assume that your system is isolated, even if it was not written, even if this was not written. Let's say this it was not written. That's our assumption. We need to assume that the system is isolated. Otherwise, we cannot do anything. The total heat of this system is zero. It doesn't exchange heat with surrounding. The total heat, what is it? That's total heat of different component of the system: copper, water, and beaker. So the water, we know that's liquid, so we use the formula. Copper, that's solid, so we use the same formula. And beaker, it's given the heat capacity, so we don't use Cm delta T, we use capital C delta T. Okay, that's the heat capacity. So that's the way how to solve this problem. See you in my next video.